Okay, so let's pick up where we left off, which is going to be earth layers and earth structure. So you can see we've got two different little columns here. We've got your typical crust, mantle, core, and then we have like the extended version here. So what I'm going to require you to know for class is the lithosphere and asthenosphere. These are going to be two of your vocabulary words that most people tend to get mixed up on when we have these vocab quizzes. So pay really close attention to your lithosphere here, where it's going to end up ending. It cuts right across through here. So not only does it take up your crust, but it also takes up the upper portion of your mantle. So it's a two for the price of one kind of deal with your lithosphere. That upper part of the mantle, because it's so close to the crust, is going to be kind of sort of crust-like. It's going to be stronger, it's going to be more rigid, so it's looped in as part of the lithosphere. Your asthenosphere, as you see this down here, it is just mantle. Your asthenosphere, one layer, only your mantle, directly below your lithosphere. And because it's below your lithosphere, that means it's deeper in earth, so it's hotter, so it's not going to be as rigid or as strong as what's in your lithosphere. Just mantle. Okay? Not worried about this. We're just going to keep it short, sweet, mantle. You have your outer core and your inner core, which I hope we discussed in the last video because it's been a minute since I watched that. But little refresher, your outer core is going to be liquid and your inner core is going to be solid. It's going to be your biggest hints on finding those on the vocab quizzes. Your outer core, it may refer to it as molten, and molten being your fancy word for liquidy. Your inner core is going to be a solid, primarily composed of iron and nickel. Remember, we think that solid inner core, kind of just floating around doing its thing in the outer core, is going to be what generates Earth's magnetic field. You can watch this little video about how deep we've dug into the crust. I really like it and think it's kind of cool. Remember, we've only gone like 7-something miles into our crust, which is just a tiny, itty bitty little squeak compared to how thick our crust actually is. So we are very, very far away from actually breaking through it. So don't need to worry about that. So let's talk about two kind of reoccurring themes that you're going to see over and over again in this chapter. The first one being this depth increases. So does pressure and so does temperature. This should kind of be like a common sense duh kind of thing. Okay. The further you get into Earth, the closer you are getting that core, the closer you are getting to that molten outer core, it's hot. Okay. The farther down you get, hot. Think of volcanoes. There's like magma-y stuff in there. Okay. And if you're having trouble wrapping your head around that, think about it kind of like a lasagna or any other kind of food. You may be able to like touch the top of it and feel like it's nice, cool, and it's safe to eat. But when you get a part of it and you decide to actually bite into it, you're going to realize it is still like nuclear hot. It fooled you. It was cool on the outside, still a lot of heat going on the inside. Same concept with our planet. Okay, our planet's not old enough to where it's all nice and cool throughout the entire thing. If that were the case, we'd have some very different stuff going on in our world. Pressure. Pressure is also going to build up as you increase, because as you go lower and deeper into Earth, you not just have the pressure of air on top of you, which is where we have air pressure and what's on us now. You're also going to have the pressure of everything that is built up, all those other layers built up on top of you. Okay, lots and lots and lots of pressure. And I think I touched on this just a second ago, so my bad if that was a spoiler, but they think that the inner core being solid and being able to kind of have some more movement and freedom in our more liquidy outer core is going to be what provides us with our magnetic field. And again, the fancy super special term for that is magnetosphere. So little reminder from way, way back when we covered that in gravity and magnetism. This is going to be another thing that we keep coming back to and coming back to and coming back to, are convection currents. Okay? Convection currents are huge. They are going to be one of the main ways that we support evidence of plate tectonics as a theory, and we're going to keep coming back to what happens with those and that flow and cycle of heat, as well as density, and how that comes into play with all of this. So with convection currents, you're going to be needing to kind of picture what's going on in the mantle. Hopefully, you already know this by now, but heat rises and cool air tends to sink. That's why if you have a two-story house or a split-level house, you probably know that the upstairs is way warmer. And if you have a basement in your house, you definitely know that the basement is much cooler. This is also why you've probably heard some of your parents complain about utility bills being a lot higher in the winter because it's a whole lot harder to heat those lower levels and keep that heat down there because it wants to rise up to the higher levels. So heat is going to rise. Okay, so kind of picture that in the head with the mantle. So as heat rises, it's actually going to end up giving off that heat. So as part of your mantle rises, it's going to end up giving off part of that heat. Okay, so as it's giving off heat, that means it's going to end up cooling. Well, we literally just said a second ago, cool stuff is going to sink. So as it's giving off heat, it's going to start cooling, which means it's going to start sinking back down. We just said on the last slide that the deeper you get into Earth, the hotter it gets. So as it's sinking back down into Earth, it's heating right back up. And as it's heating up, it's going to start rising. So this is like a never-ending vicious cycle. Heats up, rises. As it rises, gives off heat and cools. As it cools, sinks. Heats back up, lather, rinse, repeat. So that's what's going to be happening with these convection currents. And density also plays into this. If you didn't learn about density, that's going to have to do with kind of the consistency and how compact the atoms and molecules of a given substance are. If you think back to, most of you can probably picture in your head when you were learning about solids, liquids, and gases, what they illustrated those like in your textbook. It was usually like a square for a solid with a bunch of little circles and they're all squished together in the square. Then for a liquid, you had the same little circles, but they were spread out just a little bit more. And then for a gas, you had the same little circles, but they drew them way, way, way far apart with like little swooshy motions around them. Okay, think about that with density. The more dense and compact it is, that is going to cause it to sink. The less dense something is, it's going to be able to float and rise. So you should hopefully be able to connect this density part with heat. Since heat rises, that means hot material is going to be less dense. And since cooler material sinks, because it is sinking, it is more dense when it's cooler, which should connect back to those states of matter. Typically, something is much cooler when it's a solid than when you've heated it all the way up to a gaseous level. So keep that in mind, okay? Keep those two key points in mind. Hot material is going to rise and is less dense. Cool material is going to sink and is more dense. And then here you can just see some simple pictures of convection currents in the mantle. You can see that the hot material is rising. As it rises, it cools off. Now that it's cool, it's going to sink, heat back up, and repeat the same thing we've been saying for the last few minutes. This is just a simple little video on convection currents. If you want to watch it, I think it's really well done. It has pretty colors in it, and it's a really easy, simple experiment that kind of lets you see this cycle in motion. Let's talk about continental drift. Now, keyword I want you to focus in on here is hypothesis. We talked about the difference between a hypothesis, a theory, and a law earlier. Hopefully you remember the differences between those, because a hypothesis is that lowest level, okay? Alfred Wegener, he had a great idea. He thought that all the continents were joined together maybe around 300 million years ago because he actually had some evidence to back it up. Now, let's look at his evidence before we go to this final bullet point, and we'll pick this apart a little bit. He actually had a surprising amount of evidence. So if you look at a map, you may have noticed before in the past, or if not, hopefully go look at one and go notice it. But it looks like you could take South America and kind of just fit it nice and neatly into Africa. Same thing with North America and parts of Africa and Europe. It looks like you could just kind of curve and put it right there, and they would all fit together kind of like puzzle pieces. And that kind of started him on this track of, well, let's investigate why that is. So when you kind of fit all the puzzle pieces together, you notice some mountain ranges end up lining up along through the different continents. You notice that coal fields in South America mirror where they would be connected to Africa. They're in that same kind of locale. You get deeper into this, and certain fossils like Glossopteris, which is a type of fern, you find it in Africa, South America, Australia, India, and Antarctica. Now, I don't know about you, but I've never quite witnessed a fern rip its roots up, scamper away, and like go migrate across continents. Okay? Not very familiar with plant migration. There's probably a reason for that because it kind of sort of doesn't happen. So the fact that this fern is found in all these different, very disjointed now areas, again, leads to the thought of, well, maybe they were connected a long time ago, since again, it's a fossil and it's old. Same thing with Mesosaurus and Lystrosaurus. These were freshwater reptiles found in places separated by oceans. Hopefully, your brain puts two and two together. Freshwater versus marine oceans. The freshwater organisms are not going to jump into salt water and migrate and trout. That's not going to happen. Most freshwater organisms do not function or do well at all when introduced to salt water in any form or fashion. That's why if you go to an aquarium store, you have two very different sections. You've got freshwater organisms and saltwater, and they don't exactly mix. And climate. You can find fossils of tropical plants on islands in the Arctic Circle. Again, don't know about you, but when I'm planning a beautiful, fantastic tropical vacation, the Arctic Circle is nowhere like in my top million, pretty much. So, this is why it kind of made sense to him that, okay, they're not together now, but maybe a really, really long time ago, they were all sort of formed together and close to each other, and they've since drifted apart. I say, the logic is there and the logic is sound. But he had one major problem, and that's he couldn't explain how entire continents moved. It's kind of like, okay, you got your evidence, sounds great. You had us in the first half, but when we asked you, well, how'd the continents move? And you're over here like, that doesn't really make it sound very convincing in that argument. Now, you hopefully have picked up that we do know how they moved. We do know how the continents were able to go and do their thing. It was convection currents that carried those parts of the crust. Well, poor Alfred Wegener didn't know about convection currents, so you actually technically know more about how the world works than he does right now. He wasn't able to support his claim, and that's why it was kind of left with, as a lowly little hypothesis, and it didn't take off and run away. That's where plate tectonics is a theory. It takes all of that knowledge and evidence and information in continental drift and adds convection currents and all the stuff we know today in with it. That's why it's a theory. It's got better and more evidence and explanations to back it up. Plus, there are certain little parts of it we can be eyewitnesses to. We can see it happen in the real world. So that's where he was missing and why continental drift halted as a hypothesis. Let's talk about the next two things that you may struggle or have a little bit of trouble differentiating between on your vocab quiz, which is going to be the difference between a mid-ocean ridge and a deep ocean trench. And we're going to completely and totally ignore all the bullet points on this slide for right now, and we're going to focus on the actual words themselves, and then we're going to go talk about a picture, because the picture makes so much more sense than just reading a bunch of words and bullets. So what I want you to do is looking at mid-ocean ridge, okay? You have M-O-R, more, okay? At a mid-ocean ridge, you are going to make more. And make more what, you might ask? That is going to be seafloor, okay? You're going to make more seafloor and the act of seafloor spreading. So try and kind of keep that in mind to help you differentiate between the two. We've got our picture of our mid-ocean ridge here, and this is going to have to deal with two parts of the crust, and they're going to be riding on convection currents. If you notice how the convection currents are going, they are moving in opposite directions, and they are going away from each other, okay? You've got one arrow going over here to the right. You've got one arrow over here to the left. So they are moving away from each other. Again, seafloor spreading. Usually when you're trying to spread something out, you're trying to move and flatten and move things in opposite directions away from each other. So these plates are moving away. That's going to leave a gap because what's directly under the crust? The mantle. Okay, that's like molten magma material. If you take the crust and go boop, and there's a nice little gap in the middle, that's going to leave way for that magma to rise up to the surface. And since we are saying this is mid-ocean, it's cold down there at the bottom of the ocean floor. So that water is going to help the magma to cool and create a brand new little bit of Earth's crust. So magma rise, it cools, you've created new seafloor. And these plates are going to continue to drift apart. That gap's going to widen again. New seafloor is going to end up happening. So there's your mid-ocean ridge. And another thing that you will want to know is the age of the crust around a mid-ocean ridge. If you're looking right here, directly at the mid-ocean ridge, this is the youngest portion of the crust. If you're looking way over here at the edge, that is an older portion of the crust because this is fresh. This is happening right now. And as it moves, more comes up and keeps pushing it further and further and further out. And this picture illustrates it a little bit better. You can see younger crust is going to be located right here at your mid-ocean ridge. Older crust is going to be farther and farther and farther away from it. But that's about as tricky and difficult as that gets. Okay, mid-ocean ridge, you're making more seafloor. They're moving away from each other. So let's go back for a second and talk about those bullet points on that slide now. So these mid-ocean ridges are literal mountain ranges. They're found on the ocean floor. We discovered these with the invention of sonar when we were scanning and trying to map our ocean floor. And we figured out what's going on down there. They have a split at the top. Wonder why that is. It's because it's literally being pulled apart so more magma can come up. Okay? And this again is where seafloor spreading is going to take place. This is where the new crust, when that magma once again rises up, it's going to cool and create more crust and new seafloor. Now, we said over and over the plates were moving away from each other. This is going to be known as a divergent boundary. This is one of 3 types of plate boundaries we're going to talk about in this chapter. So when they are getting away from each other, that is divergent. Think about like division or dividing. You're trying to split them up. Or if you're really just struggling with ways to like remember this, you could literally think, I'd rather die than have to be next to you, and they are trying to get away. Okay, so divergent boundary. The next thing is what you will possibly get mixed up with mid-ocean ridges, and that's going to be deep ocean trenches. Okay, now these, again, we're going to completely ignore everything on this slide, and we're going to look at the picture because the picture makes a lot of sense. But my little trick for you with remembering a deep ocean trench and what it looks like is going to probably offend any form of OCD you have, especially associated with the letter T. So instead of drawing your nice, standard, pretty little T, you're going to draw a very ugly one that looks like this. And the shape of that T is hopefully going to help you memorize the very iconic dead giveaway part of a mid-ocean trench, which is called a subduction, not subduction, subduction zone. Okay, right here for proof of spelling. But let's look at the picture. Hopefully you can see right in here. Okay, that looks like my terrible, ugly drawing of a T. This is a subduction zone. Anytime you hear that prefix sub, it means below. Okay, submarine, it is below oceans. Okay, subterranean means below ground. If somebody is submissive, they think they are of lower rank or lower stature than somebody else. So that prefix sub means below. In a subduction zone, this is where part of the crust is literally getting yanked right back into the mantle and being made into molten material again and kind of recycled to an extent. This is why I told you earlier in the first video, we're losing part of our fossil record because whatever fossil evidence, artifact, anything that's in this portion of the crust, it's fixing to go like bye-bye into hot, molten-y mantleness. And we're not ever going to get that back. So what ends up creating this subduction zone? Before with the mid-ocean ridge, that was a divergent boundary where they were going away from each other. This here at the deep ocean trench is a convergent boundary where they are colliding in with each other, and one is going to lose being subducted or pulled underneath the other one. In this way, mid-ocean ridges and deep ocean trenches, they balance each other out. Because if you just think of mid-ocean ridges, if more and more and more seafloor is being created, does that just mean Earth's getting bigger and like expanding into the infinity? No, that's not how the world works. This is what stops that from happening. As a mid-ocean ridge, the plates are being pulled apart for new seafloor to happen. The deep ocean trenches are pulling that mantle back into the crust and recycling it. So it's an ongoing balancing act to kind of keep that from, again, Earth's crust expanding into forever. Here you can even kind of see where they put a mid-ocean ridge in this drawing. They've got the plate that is being subducted. That subduction's even pulling this plate away from the mid-ocean ridge, allowing for new seafloor to be created and crust to be made. So you can see the balancing act going on here where they're going to even each other out. And that's what goes on in a deep ocean trench, okay, is subduction. And that's as difficult as this chapter or this unit, whatever you want to call it, ends up getting. If you know the difference between those two and know what happens at them, then life is good for you. Let's go back and talk about the bullet points on that slide. These deep ocean trenches, you've seen it, we've said it, they're areas where the ocean floor is going to get pulled and sinks back into the mantle. The new crust that's been created at the mid-ocean ridges, remember, hot stuff is less dense. It's brand new crust. It's just been made where the mantle has cooled off. It's going to be hotter and less dense. That older crust that's been moved and bumped along to the side, it's older, it's colder, it's denser, and it's going to get subducted, okay, whether it likes it or not. When these plates collide, it is the pull of gravity that's going to cause this older, colder, denser material to be pulled right back into the mantle. And this is called subduction. Okay? Seafloor spreading and subduction work hand in hand to balance each other out. And once more, when you have plates coming toward each other, crashing into each other, colliding, all those C words, that's a convergent boundary, which is yet another C word. So that's 2 of your 3 boundaries. And I have talked for long enough and need to let my computer charge. So I will see you in the 3rd and final video for this chapter unit thingy. Bye, guys.